I just wanted to go over a couple of the problems on the practice test that you guys didn't get to on Monday. So let's look at number 15. It says, how many moles of K plus are present in 343 milliliters of a 1.27 molar solution of potassium phosphate? So in this, you have volume of potassium phosphate, and you have molarity of potassium phosphate. So if you multiply the volume of potassium phosphate by the molarity of the potassium phosphate, you'll get the moles of potassium phosphate. Now, if you look at potassium phosphate, you can make a mole ratio. Right? You can look at how many potassium ions you have for how many moles of potassium you have for every one potassium phosphate formula unit. So, for every 1 mole of K3PO4, you're going to have 3 moles of K plus ions. And so this is our problem solving strategy. If we find moles of potassium phosphate, then we can use those moles to find the moles of potassium ions. So that's what I'm going to do now. Alright, we need to also change this volume that's in milliliters to liters. So if you have 343 milliliters of potassium phosphate, for every 1,000 milliliters, there's 1 liter. And you have 1.27 moles of potassium phosphate. For every 1 liter of potassium phosphate solution. Alright, let's shrink all this a little bit. Alright, and then finally, for every 1 mole of potassium phosphate, you have 3 moles of potassium ions. You can check to make sure your units cancel out, your milliliters cancel out, your liters cancel out, your moles of potassium phosphate cancel out, and you're left with moles of potassium ions. And so if you put this into your calculator, you'll see that you get 1.31 moles of potassium ions. Alright, let's look at the next problem. Okay, so in the next problem, you're asked to determine the oxidation state of carbon in carbon dioxide. So you need to be familiar with the oxidation state rules, right? So we have rules for oxygen. Our rules for oxygen say oxygen is going to be -2 for the oxidation state. We don't have a rule for carbon, So we don't know what carbon's equal to. So I'm going to call carbon X. And then we know that the sum of the oxidation states in an ion, this is an ion, right, because it has a charge on it. The sum of the oxidation states in an ion will equal the overall charge. So you're going to have X plus, oxygen's -2, but you have 3 of them. And this is all going to equal -2. So let's solve for X. So we have X minus 6 is equal to -2. So X is going to equal +4. So that's the oxidation state of carbon in the carbonate ion. Alright, so let's look at this titration problem. You have 80 milliliters of some unknown concentration of phosphoric acid. It requires 126 milliliters of 0.218 molar potassium hydroxide solution. What is the concentration of the phosphoric acid solution? So we want to find molarity of phosphoric acid. Remember that molarity requires moles per liter. In the problem itself, it tells you the volume that you have. So you need to find moles of phosphoric acid in order to determine the molarity, because you have the volume. You're given information about potassium hydroxide, so you want to use this information about potassium hydroxide to find out something about the phosphoric acid. So you can use that blue chart that I gave you guys in class today. So if you use the volume of potassium hydroxide, you could find the moles of potassium hydroxide. You could find the moles of potassium hydroxide, right, using the molarity. Right, and so it's the molarity of potassium hydroxide given. If you know the moles of potassium hydroxide, you could write the chemical reaction of potassium hydroxide and phosphoric acid and use the stoichiometric coefficients to find the moles of phosphoric acid. Once you know the moles of phosphoric acid, you can find the molarity using the volume that's given in the problem. Okay, so that's our game plan. So the things that you need to know is you need to know the stoichiometric coefficients. You find that out by writing a balanced reaction for this. So let's write it. So if you have KOH, that's aqueous, plus phosphoric acid, that's aqueous, yields, this is an acid and a base reaction, so it's going to yield salt and water. It's going to yield water. It's going to yield salt. The salt in this case is going to be potassium phosphate. Potassium is in group 1A, so it has a +1 charge. Phosphate ion has a -3 charge. So you're going to need 3 potassiums for every 1 phosphate. This is aqueous. Alright, so let's balance this. On the right-hand side, there are 3 potassiums, so we're going to need 3 potassiums on the right-hand side. And then there are 3 oxygens from hydroxide on the left-hand side, so we're going to need 3 on the right-hand side. There are 6 hydrogens on the product side. Now there are 6 hydrogens on the right-hand side. Okay, so we have a balanced chemical equation here. Alright, so now that we have a balanced chemical equation, we know that for every 3 moles of potassium hydroxide, there's going to be 1 mole of phosphoric acid. And so we have all the information we need to solve our problem. So the volume of KOH, that's where we're going to start our dimensional analysis. It's in milliliters. I'm going to change it to liters. So 126 milliliters is 0.126 liters. So we have 0.126 liters of potassium hydroxide. 1 liter of potassium hydroxide solution. There's 0.218 moles of potassium hydroxide. For every 3 moles of potassium hydroxide, there's 1 mole of phosphoric acid. So if we calculate that, we get 0.00915 moles of phosphoric acid. Okay, we have moles of phosphoric acid. We want to find the molarity. So the molarity of phosphoric acid is going to be equal to these moles, right, divided by the volume here. So we have, and the volume needs to be in liters because molarity is in units of liters. Divided by 0.080 liters. Right, so you put that in your calculator and you should get 0.114 molar. So the concentration of the unknown phosphoric acid solution is 0.114 molar. Alright, let's look at number 18. Let's classify each one of these reactions. So the first one, you have something that has hydrogen in it. So it's hydrogen bonded to this nonmetal. This is an acid, right? So this is hydroiodic acid. And then you have another thing, lithium hydroxide. This lithium hydroxide has an OH group. So that means it's a base. So you have an acid and a base in the reactants. And then you look over in the products. You have lithium iodide, that's a salt, it's a metal and a nonmetal. And you have water. So an acid plus base yields salt and water. So that means that this is going to be an acid-base reaction. So that's what you need to look for in an acid-base reaction. Let's look at the next one. In the next one, you have sodium chloride dissolved, right? It's dissociated. It's in a solution. And you have silver nitrate also in a solution. When you mix these two, you get silver chloride and sodium nitrate. The silver chloride is a solid, so a solid forms when these two liquids mix. So this is a precipitation reaction. So something precipitated out of solution, the silver chloride. Let's look at the next one. The next one you have lead acetate, lead 2 acetate, and sodium chloride. Both of these are aqueous. You put them together in a solution and you get a solid, lead 2 chloride. The solid precipitated out of the solution. So the solid here, lead 2 chloride is telling you that this is a precipitation reaction. So these are the things you need to look at when you're trying to decide, when you're classifying what kind of reaction it is. Let's look at the next one. So for the next one you have solid magnesium reacting with hydrochloric acid. This is what you did in lab, incidentally. So for this one, hydrochloric acid is an acid. Magnesium is just a solid metal. So this cannot be an acid base. Look at the products. You have aqueous and gas. These cannot be a precipitation reaction because a solid didn't form when these two things reacted. So the other kind of reaction is an oxidation-reduction reaction. So this is going to be a redox reaction. And you can confirm that it's a redox reaction because you can look and see if something gained or lost electrons. For example, magnesium here is has a zero oxidation state, right? Because it's just the magnesium metal by itself. It's the element by itself. Over here on the right-hand side, you have magnesium chloride. Magnesium chloride is aqueous. That means it's dissolved in some water. So that means that that magnesium in there is an ion. So you have Mg2+. Remember your rules say for a monoatomic ion, the oxidation state is going to be equal to the charge of that ion. So magnesium has a 2+ charge on it. If magnesium goes from a 0 charge to a 2+ charge, magnesium is oxidized because it loses electrons. So you just confirmed that this is in fact, a redox reaction. So in this reaction, right, magnesium is oxidized. For practice, let's just find out what is reduced. So here on the reactant side, you have hydrogen. We said that hydrogen is going to be a +1. So that means that chloride is a -1. We go over here on the products. Since this magnesium chloride, this magnesium chloride is going to dissociate in water. And so we're going to have -1 for the chloride. So nothing changed. And so here, if we look at H2 gas, the oxidation state is going to be 0. So, on the reactants, hydrogen has an oxidation state of +1. The reactants, it has an oxidation state of 0. So it went from something more positive to less positive. So hydrogen is reduced. Because it gained electrons. So you confirm that it was in fact a redox reaction. Okay, let's look at 19. It says, what are the spectator ions in the reaction between potassium hydroxide and nitric acid? So let's write out the molecular equation first. So we have potassium hydroxide, so aqueous, plus nitric acid, aqueous. Potassium hydroxide is a base. Nitric acid is an acid. So this is an acid-base reaction. So it's going to give salt and water. I'm going to write the water first, plus the salt. The salt is going to be potassium nitrate. Now, potassium has a +1 charge on it. Nitrate has a 1- charge on it. So they react in a 1-to-1 sort of ratio. This is a balanced equation, but you need to check right before you move on from the molecular equation to the ionic equation to make sure that it's balanced. Alright, so everything that is aqueous can dissociate. So you have K plus OH minus plus H plus is aqueous plus NO3 minus. This yields, I'm going to write the products in a different color. H2O, which is a liquid, plus K plus NO3 minus, that's aqueous. So we're going to cross out we're going to look for anything that doesn't do anything and cross it out. Okay, so potassium on each side doesn't do anything. Nitrate, right, also doesn't do anything. So potassium and nitrate are the spectator ions in this particular reaction.